Hey, good morning or good day. Good afternoon, everyone. This is lecture 17 of 124-104 Physics 1A, where we will learn still about angular momentum, but we will look at using the cross product to find the angular momentum of particles. And then we will also apply the cross product to finding torques and allowing us to calculate more sophisticated three-dimensional torque problems. So let's just review what we've learned yesterday about angular momentum. So we learned that if a rigid object rotating about a fixed axis will have an angular momentum. So the angular momentum is given by this equation. It's relating the angular velocity with the moment of inertia of the object. So yesterday, what we considered are really rigid objects that rotate about a fixed axis. For example, this disk that's rotating about a fixed axis. Then we can easily define its angular momentum by determining its angular velocity and its moment of inertia. But how about for situations where you have a particle such as this, and this particle is rotating? So it has circular motion like this. So it's quite different from the extended object we've seen yesterday, like the disk that is rotating about a fixed axis, right? So this in this lecture we'll look at how we calculate the angular momentum of this particle as it undergoes circular motion. So a little bit of revision about circular motion that we've learned before. So when the object undergoes circular motion like so, it will have some linear velocity, and the linear velocity is tangent at each point of the circular path. So if the object is at this point, then the linear velocity will be pointing to the left, tangent to the circular path. At this point, the linear velocity will have a different direction, which is again tangent to the circular path. So because your object has linear velocity, then your object will also have linear momentum. And we learned that linear momentum relates the linear velocity v to the mass m of the object. We also learned that as the object is undergoing circular motion, it will have some angular velocity. Okay, so the angular velocity is determined by using the right-hand rule. You curl your fingers in the direction of motion. So in this case, the particle is moving in the, anti-clockwise direction, like this, anti-clockwise direction. And so the direction of angular velocity is given by the thumb, which we represent as this dot, meaning you can look at it as an arrow that's pointing outward, out of the board or out of the page. Okay, and we can relate the angular speed of the rotating particle to its linear speed via the radius of the circular motion. Yeah. Okay, so then if we want to find the angular momentum of this rotating particle that has some linear velocity, then we can also still use the general definition for angular momentum, which is the moment of inertia times angular speed. This time, the moment of inertia can be defined as the mass times the distance of the mass from the axis of rotation. So in this case, that's r. So this is the general definition of moment of inertia, right? It's mass times distance from the rotational axis squared. Okay, so this is general definition of moment of inertia, I. Okay, and the linear speed is related to the angular speed, as I've shown in the previous slide. So therefore, we can write the angular momentum using the definition for moment of inertia and the definition for angular speed. Okay. So we can simplify this. The R will cancel, we'll cancel one of the R's here. And so we have the angular momentum being equal to R times M times V. So if you can see here, M times V, this is equal to the linear momentum. Okay. The angular momentum of the particle that's moving in the circular motion is therefore equal to the radius of the circular path, okay, this R, times the linear momentum of the particle. Yeah. Okay. But angular momentum is a vector. Right? We've learned this yesterday. So in vector form, the angular momentum of the particle undergoing a circular motion is the cross product of the radius of the circular path and the linear momentum of the particle. So R, so let's define the variables there. R, that's the radial distance from the particle to the axis of rotation. It's essentially, if you trace this particle, it's undergoing a circular motion. It's essentially the radius of the circular path of the particle. And P is, of course, the linear momentum. And this cross here, this is not multiplication. This is the cross product. So the angular momentum of the particle that's undergoing circular motion is the cross product between the radial distance or the radius of the circular path and the linear momentum of the particle. Right. You've learned cross products in math, I assume. Yeah, good. Right. So let's probably just do a quick revision. What is the cross product? The cross product involves two vectors. Yeah. Say vector, in this case, vectors R and P. But in general terms, if you get the cross product between vectors A and B, the resulting vector C will also be a vector. That's why it's also called a vector product. And so to find the magnitude of the resulting vector C, it's defined by a sine theta function. So that will be multiplying the magnitudes of the vectors that are being crossed. Magnitude of A times magnitude of B times sine theta, where theta is the angle between the two vectors that are being crossed. So to find magnitudes, simply use the sine theta function, AB sine theta. Finding the direction, so when you do a cross product between two vectors, the resulting answer will also be a vector. So to find the direction of the vector resulting from the cross product, we need to use the right-hand rule. And we'll see what the right-hand rule is all about. But just some notes, some special properties about the cross product. You probably already know this, that the cross product of two parallel vectors is equal to 0 because essentially the angle between them is equal to 0, and sine 0 is equal to 0. And the cross product of a vector by itself is 0, again, using the same argument where if you're just crossing the vector by itself, then the angle will be 0 and sine 0 is 0. The cross product or vector product is not commutative, meaning the order for which you cross the vectors is important. So A cross B is not equal to B cross A, particularly in terms of the direction that results from the cross product. The magnitude will probably still be the same in some instances, but the direction will definitely be different if you exchange the order of the cross product. And that's why the order of vectors is important. Cool. All right, so let's see how we find the direction using the right-hand rule. So there are Yeah, there are many methods of doing the right-hand rule. You probably learned something in school. And if you search the internet, there are many methods. So the first method is using the cross, the curling. I want to call this the curling method, where you curl your fingers from A to B. So if you're crossing the vectors A and B, a vector A is pointing to the left and vector B is pointing out of the page. So you sort of get your right hand, that's why it's called the right hand rule. Point the four fingers in the direction of the first vector and curl your fingers in the direction of the second vector. Second vector is pointing outwards towards you, and the thumb points in the direction of the cross product result. So A cross B will have a direction of upwards. The second method I want to call the slap rule, because so you point your four fingers in the direction of So your thumb points in the direction of the first vector A, and your four fingers point in the direction of the vector B, and you sort of slap in the direction of A cross B. That's why I want to call it the slap rule. And so A cross B will have a direction of out of the page or towards you. And the third method, I want to call it the three-finger method, where you use your three fingers. Your three fingers form right angles with themselves. So the first vector is represented by the thumb, the second vector by the forefinger, and the resulting cross product is represented by the middle finger. So A is upwards, B to the left, and A cross B is pointing to you. So you can use any of these right hand methods. I have a fourth method, which is usually what I use, especially if you don't want, to rotate your fingers. So you can use this method where you draw the coordinate axis. So coordinate axis, I hat representing, plus X, that's the plus X axis. J hat, that's the plus Y axis, and K hat, that's the plus Z axis. So of course, going backwards here, you have minus K hats or minus Z axis. Okay, and then pointing to the left, you have minus I hat, or that's the minus X axis, and pointing downwards, of course, that's the minus J hat or minus Y axis. Okay, when you're crossing two vectors, the cross product involves two vectors all the time. It's always involving two vectors at a time. The answer will be the third vector that's not involved in the cross product. And if you're doing the cross product in the clockwise direction, then the resulting cross product will have a negative sign. If you're doing the cross product in the anti-clockwise direction, the resulting cross product will have a positive sign. Okay, so let's look at an example. Say, for example, you do, I have, say, J hat crossed with I hat. Okay, so you are using J hat and I hat as the vectors that are being crossed. The answer will always will be K hat, will be the third vector that's not involved in the cross product. And to find the sign of K hat, you sort of go to your coordinate, to your axis. And if you do J hat crossed with I hat, you're sort of crossing, going from J to I, and you're moving in the clockwise direction. When you're crossing J to I, clockwise means negative, so the answer is minus K hat. All right. Okay, if you want to cross, for example, minus I hat crossed with K hat. Okay. So you're using I hat and K hat as the cross product vectors. The answer will be J hat because it's the only unit vector that's not involved in the cross product. Now to find the sign of J hat, you go to your coordinate system. So I hat is in this direction, yeah? So that's minus I hat. Okay, minus I hat, you're crossing that onto K hat. Okay. So when doing the cross between minus I hat into K hat, you're moving in the anti-clockwise direction, and therefore this should be a positive J hat. Yeah, okay, right. Got that, yeah? Cool, let's do some practice. Right, so here are 4 vectors, A, B, C, D, their orientations are shown, and find the directions of these cross products here. A cross D, B cross D, C cross B, and C cross C. So your answer, yeah, a choice of answers are either this one. So K hat represents out of the board or going into your direction, into the board is minus K hat, or going into the page, into the board. Okay, A here is plus J hat. B is minus J hat. C is a diagonal vector, so we should expect that it will have some components. So vector C, you can get the X component. It will have a minus I hat component and a J hat component. So C will be minus I hat plus J hat, and the D, vector D, will be I hat, right? Okay, so let's do A cross D. A cross D, you're doing essentially J hat crossed with I hat. So if you go to your coordinate system, you're doing J hat crossed with I hat. To do the cross, you're doing a clockwise cross from J to I hat. So naturally, your answer will be K hat, but you're doing clockwise. So that will be a minus K hat. And minus K hat is going into the board. Yeah. Right, B cross D. B cross D, you're essentially doing a cross product between minus j hat and I hat. Okay, so you're doing minus j hat is a downward vector and I hat is to the right. So you're going minus j cross to I hat. You're using I and j hat, therefore the answer should be a k hat. But to do the cross, you're doing anti-clockwise because you're going minus j to I hat. So that will be a plus k hat. Right. Okay, C cross B, you have minus I hat plus j hat crossed with B is minus j. Right, but as I've said, you can break down vector C into an I component and a j component. Since you're crossing C with B, and we said that if two vectors are parallel or anti-parallel, their cross products is 0. So you're essentially just getting the cross product between minus I hat and minus j hat. So you're essentially just getting minus I hat and minus j hat, the cross product between these two. Okay. So you're going from minus I hat to minus j hat. That's an anti-clockwise direction. So the answer will, of course, be k, because k is the only vector that's not involved in the cross product. But when doing the cross product, you're going anti-clockwise from minus I hat to minus j hat. So that should be a plus k hat. Or out of the page. Right. And of course, C cross C is 0. Yeah, cross product of vector with itself is 0. Right, are we okay with this? Getting the directions like this? Right, good. Now, sometimes we will also do cross products of 3-dimensional vectors. And I'm pretty sure you learned this in maths. Good, how to find the cross products using the determinant. You can use this matrix and put your values for your I, J, K vectors in matrix form. And if you want to get the I hat component for the cross product, you sort of cover, the I column, and you're just getting the cross product between j hat and k hat. So the cross product between j hat and k hat will give you the I hat vector. So to get the cross product between j hat and k hat, you get the determinant between these vectors ay times bz. So that's that part here, minus az times by, that part here. So that gives you the I hat component. If you want to get the j hat component, so to get the j hat component, it has to be a cross product between the I hat and the k hat vector. So it will be useful to sort of propagate your matrix and write your I hat column here. Cross product between k hat and I hat will give you the j hat component. So to get the cross product between k hat and I hat, you get the determinant of these two column vectors. So you go az times bx, that's that component there, minus ax times bz. So that's that component there. Will give you the j hat component. And for the k hat component, the k hat component should be a cross product between I hat and j hat. So cross product of I hat and j hat will give you the k hat component. And to get the k hat component, you get the determinant of the I hat and j hat vectors. So you go ax times by, that's this term here, ax times by, minus ay times bx. So ay times bx, which is this one here, is this term here. So in 3 dimensions, your cross product will have I hat, j hat, and k hat components. All right, cool. Hopefully that was just revisions from maths. Now going back to angular momentum for particle, the angular momentum is the cross product between the, for one particle, for one object undergoing circular motion. The angular momentum is the cross product between the position vector r, which defines the radius of the circular motion, and the linear momentum p. Now, if you have more than one particle, so in this figure here, you have 3 particles with masses m1, m2, and m3. To get the total angular momentum, get the angular momentum of each by doing r cross p, and then add up all the angular momentums. And so you have momenta. So you have this summation symbol here, which says that to get the total angular momentum, you add up the angular momentum of mass 1 plus the angular momentum of mass 2 plus the angular momentum of mass 3. The angular momentum of each mass is, of course, obtained by getting the cross product between the position vector r and the linear momentum p. All right. Okay, so let's look at an example to apply cross products to find the angular momentum of, in this case, 2 particles. So 2 Jaffa balls, they're rotating at high speeds in a centrifuge to coat their surface with food coloring. Each candy has a mass of 200 grams or 0.2 kilograms, and we are given here the position vectors. So this is the rotational axis O, and from the rotational axis, the Jaffa ball is rotating in this way, and the linear velocity of the Jaffa balls are given. So it's sort of like the scenario is sort of like this. The axis of rotation is on my elbow, and you have these 2 Jaffa balls, and they're rotating this way, right? In high speed. Their linear velocities are given here. So v1, right, and v2. So in this situation here, sort of they're rotating like this, but they're sort of in this position here where, which one? V1 is going in your direction, that's plus k hat, and v2 is going in the opposite direction, right? So they're in this position here. In this position, the distance of this mass 1 from the axis of rotation is this r. So my arm defines r. For this Jaffa ball, r is minus 1 I hat plus 1 j hat. So if you look at my arm is a diagonal vector. It will have a j component and an I component, right? J hat component and I hat component. Yeah. Similarly, for this Jaffa ball that's moving towards the board, the R vector will also have a J component and an I component, but this time the I component is negative because the I component is pointing to, maybe I got the signs wrong because I'm of course facing you. Yeah, so this Jaffa ball will have a minus I component. This Jaffa ball will have a plus. Oh, I have it again wrong. This is to the right. So this is plus I component, and this is to the left. So this is minus I component. But both of them, their R's have a plus J component. One of them has a minus I component, and yeah, the other one has a plus I component. right? So that's sort of like the scenario. And this figure sort of represents that scenario. And we want to find the total angular momentum of the two balls as they rotate in that direction. Okay, so let's tackle this problem. So the angular momentum is the cross product between the r vector, the position vector, and the linear momentum. Okay, so we are given here, we're given the mass, we are given the r vectors, the position vectors for each of the balls, and we're given the linear velocity vector. So it's only one k component. So given the mass and the linear velocity, we can find the linear momentum. Yeah, linear momentum is mass times linear velocity. So for the Jaffa ball that's moving in the k hat direction, we have the mass times 80 meters per second in the k hat direction, giving you a linear momentum of 16 kilograms meter per second in the k hat direction. Right. For the second Jaffa ball that's moving into the board, you'll have the mass times the linear velocity minus 80, because you have a minus k hat direction. So you have minus 80 meter per second, giving you a linear momentum of minus 16 kilogram meter per second, k hat direction. All right, so first let's get the angular momentum for the ball one. So that will be R1 crossed with the linear momentum of the ball one. So R1, that's minus I hat. So I remove the units temporarily, just so it's not so cluttered, right? So R1 is minus I hat plus J hat. Yeah, we cross this with P. P is 16 K hat. Right, you can choose to use the determinant rule, or you can distribute K hat to each of the components of the parentheses. Here, both methods are valid. So I'll just use the determinant rule to apply what we've learned in the previous slide. So you sort of build your matrix for the I hats. So this one will be R, and this one will be the P vector. So I hat for R is -1, J hat is 1, and it doesn't have a K hat component. And for the linear momentum P1, it has no I and J components, it only has a K hat component. Right. So then, therefore, the angular momentum for the ball one, using the determinant rule, it will have an I hat component. So I hat component, you sort of block the I hat column and get the determinant of columns J hat and K hat. So you'll have 1 times 16, that's 16 minus 0 times 0, that's 0 for the I hat component, yeah? Plus, for the J hat component, you have to cross I and K. So you can copy over your I hat column over here. Okay, to have the J hat component, you need to do the cross product between K hat and I hat. So you go, that's 0 times 0, that's 0 minus -1 times 16. That will be the J hat component. Yeah. Plus the K hat component. So for the K hat component, you block the K column and get the determinant of columns I and J. So for the K hat component, you have, well, -1 times 0, that's 0 minus this one times 0, that's still 0. That's the k hat component. So then you can simplify. The angular momentum will therefore be 16 I hat plus 16 j hat. Yeah, for the j hat component, the negative signs multiply each other out. The unit for angular momentum is kilogram meter squared per second. Cool. Right, we okay with that? If we're okay with that, we can then get the angular momentum for ball 2. We'll do the same thing for ball 2. The angular momentum is the position vector 2 crossed with the linear momentum 2. So that means, yeah, R2 is here. That will be I hat plus j hat. Again, I temporarily remove the units. Cross that with P2. P2 only has a k hat component minus 16 k hat. Okay. So again, I use the determinant rule. So yeah, I write down my I hat, j hat, k hat columns for vector R1, R2 and P2. Okay, R2 only has I and j, that's 1 and 1 and 0 k component. P2 vector has no I and j components. It only has a k component of minus 16. Right, so when I do the determinant method, okay, to get the I hat component, again, you sort of cover the I hat column and do the determinants between j hat and k hat column. So you go 1 times 16 will give you minus 16. Right? And minus 0 times 0 will give you 0. That's the I hat component. J hat component, you block the j column and get the determinant between k and I hat, so you sort of can propagate the I hat column after the k hat and get the determinant. So you have 0 times 0 is 0, minus 1 times 16 is negative 16. That's for the j hat component. And for the k hat component, of course, get the determinant between I and j columns. That will be 0 minus 0 k hat. So if you simplify that, you have minus 16 I hat, okay, plus 16 j hat kilogram meter squared per second. Right? Cool. All right. So I'm running out of space. So let me just do this part here. So therefore, the total angular momentum will be L1 plus L2. Okay. So yeah, we've solved for each of L1 and L2. So L1 we found earlier to be 16 I hat plus 16 I hat. Okay, again, I temporarily remove the units. Plus L2 is minus 16 I hat plus 16 j hat. Right? Okay, so it's now just combining i's together and j's together. So 16 I hat minus 16 I hat will give you 0, and 16 I hat plus 16 j hat plus 16 j hat will give you 32 j hat. That's total L. So the total angular momentum is 32 j hat, and the unit kilogram meter squared per second. Okay. Okay, any question about how we did this? Yeah, right. So I guess, yeah, I think we're fairly okay with cross products, which is good. yeah, just this is the slide for the alternative solution where you do the distributive rule, but I will not go over this. You can just distribute k hat to each of the components here and do the cross product. But yeah, we did the determinant rule. You should get the same answer. Right, so moving on with torque. So torque is also actually a cross product between two vectors. We already learned about torques before when we defined torque. Torque is equal to RF sine theta, right? This was the definition for torque that we've seen before, where we said that it's the product of the moment arm times the force that causes the rotation times sine the angle between the moment arm and the force vector. But this definition of RF sine theta being torque actually came from the general definition for torque being R cross F. It's again the cross product between the moment arm R or position vector R and the force vector, the force that will tend to cause the rotation on the object. Okay, so this specialized definition, RF sine theta, this is useful mostly in two-dimensional cases where we can easily get the perpendicular distance between the force and the moment arm, like we've always done. But if we want to consider three-dimensional problems, this cross-product definition of torque gives us a more powerful way of solving torques. So just a few notes. So the direction of torque is will actually come from the cross product from the right-hand rule that we learned. The clockwise or the anti-clockwise direction, this is the rotation, the direction of rotation that the force will create on the object. But the direction of torque is different from the direction of rotation. So we just assign clockwise rotation to be negative torque and anti-clockwise rotation to be positive torque. But the actual direction of the torque will come from the right-hand rule between R and F vectors. All right, so applying the general definition here, say you have this extended object and its axis of rotation is O. This is sort of like the pivot point or the point over which the object will rotate about. If you apply a force F1 in this direction and F2 in this direction, you can of course get the moment arm. The moment arm, this is the moment arm or lever arm R that we learned before. It's the distance from the pivot to the force, and this moment arm should be perpendicular to the force. So if we use the definition for torque being the cross product between the moment arm and the force, we result to the special case where the torque is just equal to the moment arm d times the force, because we are able to get this perpendicular moment arm relative to the force. Okay, the force F1 will tend to rotate the object in the anti-clockwise direction, and therefore the torque is positive. So if you have an anti-clockwise rotation, notice how if you do the right-hand rule, curling your fingers in the direction of rotation, your thumb will point in the direction of the torque. So the direction of the torque is out of the page, which corresponds to a anti-clockwise direction. Okay, and we do the same argument for force F2. Okay, so this is anti-clockwise. For force F2 will tend to rotate the object in the clockwise direction about the pivots or the point of rotation. If we do the torque, if you calculate the torque, it's the cross product between the moment arm and the force F2. In this case, again, we're looking at the special case because we are able to find the moment arm, which is perpendicular to the force and passing through the pivot. So the cross product reduces to the multiplication between the moment arm D2 and the force F2. The force will tend to rotate the object in the clockwise direction, and therefore you have a negative torque. Okay. A negative torque. And if you do the clockwise rotation, notice how your thumb points into the page. So the direction of the torque will be into the page. So it's quite different. The rotational direction is clockwise, but that clockwise rotation is due to a torque that is directed into the page, which gives you this negative sign. All right. Okay, so let's look at an example. Oh, yeah, of course, the total torque will be the sum of the individual torques. So here's an example. Say you have here a force vector F that is along the x-axis. So you only have a high I hat component, and the lever arm has this position. It has a component of I hat and k hat. Right. So find the torque that's generated by this force that's acting in the I hat direction. It's a relatively straightforward application of the definition. Torque is equal to R, the lever arm, times the F, the force F. The lever arm, the only difference is that the lever arm in this case has I hat and k hat components. So you need to cross that with the force which has a I hat component. Right. In this case, it's just easier to do the distributive rule and do the cross product in for each term in the parentheses. So you have here 2.2 I hat crossed with 150 I hat, which you straight away know is equal to 0 because you're crossing the vector I hat with itself. Okay. And you can also you distribute this I hat into the second term, 1.2 k hat crossed with 150 I hat will give you 180. 1.2 times 150 will give you 180, and then do the cross product, k cross I hat, you have k hat crossed with I hat. The answer will of course be j hat. It's the only vector not involved in the cross product, but when doing the cross product, you're going in the anti-clockwise direction from k hat to I hat, and so that's a positive j hat here. So torque will be 180 Newton meters j hat. Right. Okay. So yeah, so for these problems, it's really just a straightforward application of the cross product. You can try this exercise. The force is given. It has I and j components. So the scenario is sort of like this, where you have the sign. Sign is going out of the page. That's the sign here, and there's a force coming from a wind. So the force has I and j components. That means if you visualize the wind, it's sort of oriented in this direction. So it has j component, a minus j component, and an positive I component. So the wind force is in this direction, and the R, the moment arm, will come from the axis of rotation O up to the center of mass. So if you visualize the moment arm sort of looks like this. Yeah. So the moment arm is expected to have a j component, an upward component, and a k component going out here. So that's sort of the scenario. The force is from the wind blowing in this direction with I hat component and minus j hat component. The moment arm is coming from the axis of rotation at the base of the signpost. It will have a plus j hat component and a plus k hat component like this. So it's sort of like a three-dimensional problem. So the crux of the problem here is just finding r, writing the moment arm vector, but the moment arm, which is this, will have a j hat component, which is 8 meters j hat plus 6 meters k hat. All right. And I leave it up to you to find the torque. Torque is R crossed with F. This is the R, the F is given here. So do the cross products between R and F. R, of course, has a R has a j hat component and a k hat component. F has an I hat component and a j hat component. Do the cross product and see if you're able to get this answer here. Right. So yeah, I'll leave you with this exercise because it's 12:50. So you can do this exercise to practice doing the cross products. And oh yeah, we still have a lecture tomorrow. And maybe we can look at the solution tomorrow before we start the lecture. But I wish you a good day, everyone, and I'll see you tomorrow in the lecture.